right, we are now recording. Before we get started and all the visions coming up, there were a few announcements I printed off, but every one of you received these emails. So I'm just telling you, if you haven't seen them, get out there and see them. 3 of them all pertain to Fred's coming in, okay? All right. The first of these that I printed off was from our Senator Doug Jones, and he's reminding, and I don't know to whom he sent all this, but it was forwarded to us from our career services person. The Alabama State Department of Education teams up with Alabama Possible to host college application free, this is cut off. If you go to your email, you'll see the whole thing. So in other words, if you're applying to go to a 4-year school, I believe this is the week that you can get free application for selected colleges. But nowhere home here does it say when the week begins and ends. But it's coming, I think it's either coming up very soon or it has already started. On the 5th, okay, and it goes through something like the 10th or so. Okay, so the schools that they list here are Justin College, Alabama A&M, Alabama State, Auburn, it must be Auburn University at Montgomery, Fortis College, Huntington College, Jacksonville State University, Judson College, Marion Military Institute, Miles, Selma University, I didn't even know who it was one, Spring Hill College, Stillman College, Talladega College, University of Alabama, Troy University, Tuskegee, University of, this one's cut off. I see there's a Montevallo, but there's another one that starts with MO. Is there University of Mobile? I've never heard of it, but whatever. Check your emails. You've all got the email. University of South Alabama and University of West Alabama. Okay? So there's more information on transfer, admission, and scholarships. And you can see Miss Haley, who's down in, she's on both campuses. I didn't see her in the office today, but I have seen her. She's down in the student development area that's just next to student financial aid. Hers is the office right next to that little computer lab they have down there. And then, following up on that, Jacksonville State sent this, say they're proud to participate in Alabama's college application week by waiving the $35 application fee November 4th through the 8th for Jacksonville State. So you're running out of time. That's this week, okay? The promo code is JAX2020. So check your email. You got this email as well. And then this is where I saw it. This is University of Alabama celebrating Free App Week, running November 4th through the 10th. So different schools made, like Jacksonville State, in the Friday, Alabama goes through Sunday, okay? So, anyway, check your emails. All this information is there. And share it with people. And Doug Jones, in his letter, he also said the 2-year colleges are all free. There is no application fee. So share that with people that you know. You can apply there with us anytime and take it over. So, all right, those are the announcements I had time to print off, and evidently there's some pretty serious writing on the board. Pretty unserious erasing. Oh no, it's study student on the board, so maybe she did before this class. Okay. Any questions on anything before we get started today? We are already started, but those were announcements. All right, we'll pick up from current slide. And we're at, some people here probably did not get the test from the chapter 8, right? That was the last chapter, right? I'm teaching so many classes I can't keep up with the chapters of which. Oh, this is L1. L2. There's my test 2, but I only see one copy. My work study studio has been rearranging things so I can't find anything. Did everyone here get tested? Oh, you did. So I may be searching in vain. Okay. So everybody has it. All right. So we're in Chapter 9, Infinite Series, Sequences and Series, and 9.1 is Sequences. We're on page 591, top of the page there, and this is where we pick up today. So no questions or anything up tonight. Okay? Devin did ask about the WebAssign, and the guy said to me, he said you can log in and get the codes. Well, I don't use WebAssign, so I haven't logged in, so I just assumed he meant y'all can get the codes too. I'll have to go and check back with them and see. No one had said anything to me, so I thought they were all there. But probably a lot of you aren't using them because, frankly, between the 3 websites the book provides, WashingtonCalculus.com, CalcCheck.com, and CalcView.com, I can't see too much more the WebAssign could offer, but it'll be there as soon as I can get the codes from them. He just said, I finished doing it, log in and get them. So, well, go for it. All right, so sorry about that. I thought no one had said anything to me, so I thought they were all out there. So here is something, if you had been doing finite math, you would have already hit this. But in the algebra sequence, calculus sequence, these kinds of things, quite often you don't run into this until probably sometime like now. Have y'all ever run into factorials before? Yeah? Okay, well then y'all have it. The symbol in factorial, and that's what it stands for, that exclamation point, is used to simplify some of the formulas. The n can be a positive integer. Can't be a fraction, can't be a decimal, can't be an irrational number or a rational number. It has to be a positive integer. Can't be negative. It has to be a positive integer. Okay? And I would say a positive integer greater than 1, or 1 or greater. Okay? Well, positive integer would be 1 or greater. I'm sorry. We'll get to 0 in a minute. Okay, then n factorial is defined as this. Give me a number n, any number, positive integer. 5. In fact, 5 factorial would be 5 times 4 times 3 times 2 times 1. Or the way they put it here, 1 times 2 times 3 times 4 times 5. Up to n. It's every integral factor up to n, including n. As a special case, it's bizarre, but it's true, 0 factorial is defined to be 1. Of course, 1 factorial would be 1. 0 factorial is also defined to be 1. Very seldom will you need it, but occasionally you do, especially in statistics. You need that, so they define 0 factorial as 1. And by the way, I think I may have said earlier, but not everybody was here. I apologize for my voice. Yesterday, I just started getting a sore throat, and the voice is getting worse and worse all the time. From this definition, you can see that 1 factorial is 1. That's just 1. Okay. 2 factorial would be 1 times 2 is 2. 3 factorial would be 1 times 2 times 3, which would be 6. And they keep going. Now, especially when they start this way, it doesn't seem like it's a very big deal. But I guarantee you, when you get very many numbers in there and you're multiplying each one, they grow really fast. Okay? Factorials follow the same conventions and order of operations as exponents. That is just as 2x cubed and 2x cubed imply different order of operations, so does 2n factorial, okay? That's what they're saying, the factorial treat like an exponent, okay? And please excuse my dear Aunt Sally in exponents, okay? In factorials, okay? Please excuse, I can't think of what you use for factorials. Look, friendly Aunt Sally, whatever, okay? 2n factorial would be 2 times n factorial. But 2n factorial would be multiply up to get 2n. If you gave me 5, this would be 10 factorial. It would be 10 times 9 times 8 times 7 times 8. I usually count the other way. Oh, here they're doing it. The book seems to count this way. So 2n factorial would just be 2 times n factorial. So if this was 5, it would be 2 times 5 factorial. So 1 times 2 times 3 times 4 times 5. Okay? And multiply that by 2. Whereas 2n factorial would be 10 factorial. 2 times 5 factorial would be 1 times 2 times 3 times 4 times 5 times 6, all the way up to 10. Notice you don't just do the even integers, you do them all. Okay? 1 through n, 1 through 2n. And this one, you multiply the result by 2. Those are very, very different numbers. Incredibly different numbers. Okay. Another useful limit theorem can be written. Sorry, I can't talk. It can be rewritten for sequences is the squeeze theorem. You may remember this from, I think, back in Cal 1, perhaps. If you have a sequence a sub n, and the limit as n approaches infinity of this a sub n is some number L. But that's also the limit for some other sequence, b sub n, as n goes to infinity. And if those are both true, and there exists some integer n, such that a sub n, okay, yeah, go see where they got the capital N from. Some integer capital N such that a sub n little n is always less than or equal to c sub n, which is always less than or equal to b sub n, okay? Now that's saying for any single value n, let's use 5 again. A sub 5 is always less than or equal to c sub 5, it's always less than or equal to b sub 5. But these a sub n and b sub n is going to infinity, both have the same limit, but the c sub n is always in between, term by term, either in between or the same as one of those two. Then c sub n has to have that same limit. There's no way around it, you know. If every value there, a sub n is less than b sub n, or they're going to the same limit, the c sub n is also in between them, always, then it has to go into the same limit too. So it kind of makes sense. Now this, okay, I left off this part. And there exists an integer n such that these n's for all n greater than capital N. In other words, on this side of capital N, they could be all over the place. C could be here or here, whatever. But at some capital N, somewhere out here, after that, C's always in between a sub n and b sub n. Always, okay? A sub n down here, b sub n up here, up there. Back here, they could be nuts. They could be all sorts of different values here. But as for some capital N out here, everything past that, a sub n is less, b sub n is greater, c sub n is in the middle. And if these two are going to L, C's got to get to L. Because these sequences out here, they don't matter what happens back here at all. It's what happens as it's going to infinity. Okay. I have absolutely no energy today. All right. So let's use the squeeze theorem. Well, I don't know. They say we're going to use it. Show that the sequence C sub n is a set of terms, C sub n, and that's equal to negative 1 to the nth. Let me get my pen set up. And by the way, what does that do? Negative 1 to the nth. Alternate signs. If n is odd, that's a minus. Even is a plus. So that's what the negative 1 to the n does. Divided by 1 over n factorial. Okay? Show that that sequence converges and find its limit. Okay? A really easy, Mr. Maya. I think you'd hopefully be able to tell that B sub n, if I define B sub n as, well, I don't need parentheses either. Okay. Let's just define B sub n as 1 over n factorial. Not changing signs, right? Well, obviously C sub n is less than that, right? Okay. Now, I'm going to cheat a little bit here. A sub n, let's just say that's, I have no problem with saying it's 0. No, it can't be 0. Sorry. Can't be that. Let's say that is negative 1 over n factorial. Okay? So B sub n is always positive. A sub n is always negative. Okay? We got to see what's happening to the sequence. Okay? Those are pretty easy to do, I think. I would hope so. Let's just pick a few. N equal 1. Okay. N equal 1, the B sub 1 would be what? And here's Ryan. B sub 1, or he wrote it down, would be 1. C sub n would be minus 1, but A sub n, or A sub 1, sorry. A sub 1 would also be minus 1. So C sub n is in between the two. How about n equal 2? Then you would have 1/2, negative 1/2, 1/2. N equal 3. This would be, as we said before, 1/6, because 3 times 2 is negative 1/6, negative 1/6, and this would be negative 1/6. Okay? N equal 4. This would be 1 over 24, negative 1 over 24, and this would be 1 over 24. Okay? Now, these numbers are getting big really fast. The next is going to be 120. 5 times this. 6 times that would be 720. Okay? Those denominators are getting big really fast. Well, the B sub n is going to 0, A sub n is going to 0, and C sub n is bouncing back and forth between them, but never exceeding them, it's got to go to 0, too. Now, that to me would be an easy way to do it. They do it a little bit differently. You must find two convergent series that can be related to C sub n. So I guess they're saying you don't know factorial well enough to see that's going to converge. I don't see how you wouldn't. But they use 1 over 2 to the n. First with a minus, then with a plus. And we've already done that one. If you go back to your, where was it? Goodness, my throat hurts. Well, we did it in the last example. We used 2 to the n in that. But let's just let them describe it, and let's see if they make any reference to it. Because I'm tired of talking. To apply the squeeze theorem, you must find two convergent series that can be related to C sub n. Now they chose A sub n. I chose it even simpler. 1 over n factorial and minus 1 over n factorial. But they are choosing A sub n being minus 1 over 2 to the n, B sub n being 1 over positive 1 over 2 to the n, both of which converge to 0. Okay? Now, they're just saying that, so I guess we said enough earlier that you can be convinced of that. But I don't see any place that they told you that. It is true, I promise you. Okay. But you can just look at them and see. By comparing, when n is equal to 1, this is greater, of course, and negative would be way smaller, okay? Oh, wait a minute. They're not doing the same one. By comparing the term n factorial with 2 to the n, you see that n factorial after n equals 4, okay? Here's why n equals 4. You look at term by term. This one's greater here. They're the same here, but the product is greater. Okay, this is 2, this is 4. This is greater. This is 6, this is 8. But then past this is now 24. This is now 16. And notice these are getting bigger faster. These are staying at 2s. So n factorial past 4 is greater than 2 to the n. Okay? So in other words, this one will be exploding faster than this one explodes. They both explode, no problem there, but that one is exploding faster. Okay? Because these keep getting bigger and bigger and bigger, these stay being 2. So that is for n factorial and 2 to the n. Now if you invert them and do 1 over n factorial, then this is getting smaller past 4, okay? Because your denominator is bigger, your denominator here is certainly going to, getting big, so your fraction's going to 0, but this is getting big even faster, okay? So that's what they're getting at. This implies that for n greater than 4, 2 to the n is always less than n factorial. We just saw that, okay? But if you flip them, and I have to go into this, without anything else. If you flip them, then that puts 2 to the n less, because your denominators here is less than this denominator. When you flip them, that means this is always less than this. The same rule applies because you're minus sign for n greater than 4. But this is less than 1 over 2 to the n. Okay? And so therefore, after you get past, this is so ugly, here's 1, 2, 3, just a little past, but after 4, they stay in between. Here is 1 over 2 to the n, this is negative 1 over 2 to the n, negative 1 over n factorial. After you get past 4, it's always between those. Because when you invert, then that makes the denominator bigger, meaning the fraction is small, and that's going to 0. Another way to do the squeeze theorem. Okay. The factorial function grows faster than the exponential function. That's what I was trying to say. I didn't use those terms, but it did. So when you put it in the denominator, your denominator is getting big way faster, meaning the fraction is getting smaller. Okay. So by the squeeze theorem, it follows that the limit has to be 0. And there was never any question that it would be. Now, here's another, whoa. Oh, I'm sorry, I flipped too many pages. Okay. They should have led up to the next slide with a little bit of verbiage here. I thought they would, but they don't. In that example we just did, example 5, the sequence C sub n has both positive and negative terms. Okay? That's what that minus 1 to the n does for you. It alternates the signs. Okay? For this sequence, it happens that the sequence of absolute value of C to the n, also converges to 0. Okay? And that's the one that I was using for the squeeze theorem. In such cases, it's often convenient to consider the sequence of absolute values and then apply 9.4, which is what's coming up next. And here it is. For a sequence, A sub n, okay, if the limit of the absolute value of A sub n as n approaches infinity is 0, then it's got to be that the limit of A sub n is equal to 0. Because the absolute value is only going to be positive values, whereas A sub n, they could be some positive, some negative. They could be, if the absolute value is getting close to 0, then for sure, when they're alternating, or they not be alternating, but they have differing signs, that's going to have to be 0. The absolute value is usually greater than or equal to the value, right? Because if this was positive, it's the same. If this is negative, this is greater, okay? So, by the squeeze theorem, then too, the absolute value is going to 0, certainly the function itself, or the sequence itself is going to 0. Okay. Now, the next little topic here is pattern recognition for sequence. Now, this sometimes gives students the most problems. It's usually not terrible, but sometimes it requires quite a bit of mental gymnastics to do. Okay? Sometimes the terms of a sequence are generated by some rule that does not explicitly identify the nth term of the sequence. Okay? Now we saw some of these, the regressive ones. They don't. In such cases, you may be required to discover a pattern in the sequences and then describe the nth term. Once the nth term has been specified, you can investigate the convergence or divergence of the sequence. Sometimes looking at it, not going to do it for you. Remember last time, we had one that started increasing at first, but then it started increasing more slowly, but then it started decreasing. And so if you thought it was going to be, if it had a limit, it was going to be something up here, then later it did this. This up overnight. And once you leave it up too long, goodness gracious, let's see why she had trouble erasing. I have a theory of why this is happening. I think my work study student wets the board down with the Windex and then everything sticks to it. We'll see. Okay. So let's see if we can figure out what they're talking about here. Find the sequence ace of n whose first 5 terms are this: 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. What seems to be going on there? Don't lose the forest for the trees here. Let's just look at the numerators here. What's happening here? 2, 4, 8. Yeah, they're doubling every time. So if this is n is equal to 1, this is first term, this would be 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. That's 2 to the n. Okay? So there's your numerator. Your denominator, though, is what? Any pattern there? What do you see? Yeah, add 2 to the previous one. So if n is equal to 1, this would be n plus 2. So how do we express that? 1, this is first term, second term, third term, fourth term, fifth term. Looks like to me it would be 2n minus 1. Does that work? Because 2 times 1 would be 2, minus 1 would be 1. 2 times 2 would be 4, minus 1 would be 3. 2 times 3 would be 6, minus 1 would be 5. So yeah, that's your denominator. Okay. Now, then determine whether the sequences you have chosen converge or diverge. Do you think there's any doubt what this is doing? What you think? This is, well, let's just see. This is 2, 1 1/3. This is 1 3/8. This is 2 2/7. This is 3 5 whatever ninths. Okay, what you think? Seems like it's converging. Actually, it was getting smaller here. Not too certain here, but then it started getting bigger, and from there on, no question, it's going to go bigger. What you reckon? It's got to be diverging. Okay, now, this thing's growing leaps and bounds faster than that's going. Okay, numerator's increasing way faster than the denominator, so it's going to be divergent. Okay, let's see how they say it. First, note that the numerators are successive powers of 2. Denominators form sequences of positive odd integers. So this would be 2 to the n over 2n minus 1, just like we said. Okay? Now, formally, how you do that, we did it by looking at it and seeing. Formally, apply L'Hopital's rule. Okay? So first, write it into the functional form this way, rather than n's, but x's, and then see what's happening here. Well, as x is going to infinity, that's going to infinity, this is going to infinity. Infinity over infinity is one of those things that's indeterminate, so take a derivative. And as we did before, the derivative of 2 to the x is 2 to the x times log 2. If you weren't here last time, we went through that. Okay? Derivative of this is just 2. Now, this is infinity over infinity, indeterminate. This is infinity over 2, definitely infinity. Not indeterminate anymore. That is going to infinity, meaning that it diverges. Okay? L'Hopital's rule, nice little rule to have. The other thing to remember is that you can take once you have the nth term expressed in n, write it as a function of x. Okay? Well, x isn't necessarily a positive integer, but then treat it the same, because if they are going to act in the same manner, so take the derivative of that, and you can go. Hard to take the derivative of that because that's only defined for interval values. This is for all values, and you can do that. Okay. Sorry, my throat hurts so badly. Next, apply theorem 9.1. Why would you need to do that to conclude that? Oh, okay, 9.1. That was, I thought it was 9.4, the one we just did. 9.1 was the one we did last time. That if the limit of a sequence, if you, like I said, the function form, if that has a limit, so does the sequence. Okay? So if the function does that, then so does the sequence. Goes to infinity, the sequence goes to infinity. So the sequence diverges. Now, they're skipping an awful lot of stuff here. So let's go back and do some of this skip stuff. I guess we'll do it here. Top of page 593. Without a specific rule for generating terms of a sequence or some knowledge of the context in which they are obtained, it is not possible to determine the convergence of or divergence of a sequence merely from its first several terms. We saw that, okay? I'm sorry, my throat hurts. For instance, the first 3 terms of the following 4 sequences are identical. The first 2 converge, the third converges something different, the fourth diverges. So let's see what they talk about here. Here is the sequence A sub n. Okay? 1 over 2, 1 over 4, 1 over 8, and 1 over 16. Looks like a piece of cake, doesn't it? Wait a minute. Okay. All right. And comma, dot, dot, dot. Keeps going as n goes to infinity. Okay. This one is 1 over 2 to the n. The same thing we were looking at earlier. Only now it's only in the denominator. Up there it was in the numerator. Okay. That one's going to converge to 0. Right? Because as n goes to infinity, this is going to infinity, that's going to stay 1. Okay? So no question there, that's going to 0. Now, again, B has the first 3 terms the same. 1/2, 1/4, 1/8. Okay? But Things fall apart when you get to 1/15. Uh-oh, how did that happen? Okay? Well, let's see what's going on here. What would that sequence be? As long as nothing else is changing, and I don't see a pattern. Oh my goodness, where did they get that? You're supposed to recognize this? I don't think so. Okay? This is 6 over n plus 1 times n squared minus n plus 6. What? Dot, dot, dot. Keeps on heading. Okay? This one did too. I didn't put it in. Dot, dot, dot. Okay. Now, is that even true? Let's do n equal 1. This would be 6 over 2. That part would be 3 then. And when n is 1, this would be 6. So 3 over 6 is 1/2. Yep, that works. N equal 2, this would be a 3, so that would be a 2 here. And n equal 2, this would be, sorry, this would be 4 minus 2 is 2, plus 6 is 8, and 2 over 8 is 1/4. That's right. N equal 3, this would be a 4. 6 over 4 is 3 over 2. This would be 3. That would be 9 minus 3 is 6, plus 6 is 12. So 3 plus 3 times 12, 36, 6 over 36. This is 4. 4 times 12 is 48. 6 over 48, sure enough, is 1/8. That works. But then when you go up one more, n equal 4, then you get 5 here. You get 16 minus 4 is 12, plus 6 is 18. 5 times 18. 6 will go to 18 3 times. So 5 times 3 is 15. Yeah, I would recognize that one in a flash, wouldn't you? Not easy to do. Okay? But, just looking at that, the limit of this as it goes to infinity is 6. Okay? The limit of this as it goes to infinity is infinity. Okay? So that is also going to converge to 0. Not quite as obvious, but it does go to 0. C sub n. Some of these patterns are not easy to see. Starts off 1/2, 1/4, 1/8. Those are the same. But then it jumps to 7/62. Now, how in the world is that going to happen? Dot, dot, dot. Well, they just, voila, here's what it is, okay? N squared minus 3n plus 3 divided by 9n squared minus 25n. Don't be expecting to recognize these. You won't. Plus 18, dot, dot, dot. Where is that heading? You might say, hey, that can't be the first 3 terms. Can it? Well, let's see. 1, this would be 1 minus 3 plus 3, that's just going to be 1. Okay? This would be 9 minus 25. That would be minus 16 plus 18 would be 2. 1 over 2 is 1/2. That works. 2, this will be 4 minus 6 is minus 2 plus 3 is again, and this would be 36, if I'm not mistaken, minus 50. Oh, man. 36 minus 50 is 14, plus 18 is 4, 1 over 4. There it is. 3, could that possibly still work? 9 minus 9, that's going to be a 3 up there. This would be 81 minus 75. 81 minus 75 is 6. Plus 18 is 24. 3 over 18, 3 over 24, 1 over 8. Yeah. Then n equal 4. Hey, it all falls apart. 16 minus 48, no. 16 minus 12, I can't multiply. 16 minus 12 is 4, plus 3 is 7, there's your 7, and this would be 4, be 9 times 16, I'll take the word for it, that's going to be 62, okay? Yeah. So it falls completely apart there. Well, what does this converge to? Does that converge to 0? These first two did. Does that converge to 0? How do you check that? Well, you got ends up here and ends down here. What's the little test? Divide by your maximum exponent. N squared. This would be 1 minus 3 over n plus 3 over n squared, right? Well, as n's going to infinity, those go to 0. So that's just going to be a 1. Divide this by n squared, and you get 9 minus 25 over n plus 18 over n squared. Those go to 0. N get larger, they go to 0, so it would be 1 over 9. Other words, ratio of leading terms. Okay, when those are the same, that's going to be 1/9. So, has a limit. Not exactly obvious that it's heading to 1/9, but it is. D sub n. 1/2. Say 1/2 or write 1/4. I don't know what's wrong with the brain. 1/4, 1/8, and then 0. What? Dot, dot, dot. What's this going to be? Minus n. Don't expect that you're going to see these. You're not. N plus 1 times n minus 4. Over 6 times n squared plus 3n minus 2. Dot, dot, dot. Where is that going? I can tell you right now. It's going to negative infinity. Can you see why? But let's first make sure the first three terms are right. That was the fun part, right? So let's do n equal 1. That would be a 2 times minus 1 is minus 2 times minus 3 would be a plus 6. Okay? Here we have a 6. If you plug in a 1 here, you get 1 plus 3 is 4 minus 2 is 2. Yeah. And this would be 6 over 6. Those go away and you get 1/2. Yep, that works. N equal 2. That would be 3. This is a minus 2. That would be minus 6. Times a minus 2 would be minus 12. Okay? Positive 12. Positive 12. And down here you get 6, so that's going to be 2 left over here. And when you plug a 2 in here, you get 4 plus 12 is 16 minus 2. 4 plus 6 is 10 minus 2 is 8. You have 2 up here and 8 down here. It's going to be 1/4. That works. N equals 3. 4 minus 1 minus 3, that's going to be a positive 12 up here. Okay? 6 down here, so that's a plus 2 again. Put a 3 in here, you get 9. Plus 9 is 18, minus 2 is 16. 2 over 16 is 1 over 8. That works. N equal 4 though? 0. Doesn't matter what this is. That's a 0. Okay? Any n beyond 4, that's going to be positive. That's going to be positive. That's going to be negative. That's always, for large n's, that's always going to be positive. Okay? Big enough n's, it will. So you got negative over positive. It's going to be negative for sure. Now let's look at your n's. This, if you multiply them through, we give you n cubed. Minus n cubed, in fact. This is going to be 6n squared is the maximum term. What's the ratio of that? N over 6. As n's going to infinity, that's going to infinity. Negative infinity. That's a negative. So that's going to negative infinity. Just happened to be because 1, 2, and 3 kept this negative, that made that positive. Okay? And you got numbers. When it got to be 4, that went to 0, so that became 0. Anything beyond that, this is negative. This is growing faster than that. Numerator larger than denominator, going to negative infinity. So just looking at the first few terms usually is not enough. That's really encouraging, isn't it? Let's see about example 7. Nope, they don't have example 7. So let's go back and erase. And I'm sorry for those who just came in. My voice is almost gone. Started getting a sore throat yesterday, and it hasn't eased up any. So, well, the throat doesn't hurt as badly, but okay. Determine the nth term for a sequence whose first 5 terms are this: minus 2 over 1, 8 over 2, minus 26 over 6, 80 over 24, and minus 242 over 120. All right. Any guesses? Now, you may have heard me, if you've been in any of my classes before, I give this example. How do you eat a 5,000-pound elephant? Second? I can't hear. If you choose, that's your choice. But you do it one bite at a time. Okay? That's what you do. So let's take it small. First, do you see any pattern at all? Just glancing at it. Don't try to do the whole thing at once. Any little pattern. Okay, every other one's a negative. So I'm going to make a guess that we start this off with minus 1 to the n. That will produce the changing signs, right? Alternating signs. Okay?
They're all even numbers.
Okay, there's a good observation. Okay? Except this one. Okay, yeah. Okay? But the ratios are, oh no, the ratios aren't even numbers, are they? Because this is not even, that's a fractional number. Okay? But that is pretty interesting to note. Now, I've been at this longer than you have. To me, the denominators speak to me, okay? Now, what does that mean?
It means it's negative 2.
It's what?
It's negative. It starts off as negative 2.
Okay, it's negative because it's talking back to the teacher. Is that what you said? No, I don't think that's what you said. Okay. Let's look at a ratio. Ratio, this is 1 to 2 is 2. 2 to 6 is 3. 6 to 24 is 4. 24 to 120 is 5. Guess what that denominator is? What was 1 times 2 times 3 times 4 times 5? Ooh. Explanation point. Factorial, exactly. So your denominator here is in factorial. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. Okay? Again, it spoke to me. Okay. Now, how about that numerator? Now, I wonder if Patrick's idea of pulling out a 2 might be helpful. So let's play with that for a while. Forget the signs, forget the denominator, just look at the numerator. 2 times 1, 4, 13, 40, negative 121. Well, forget the signs, I said. 121. I don't know. That's not particularly speaking to me yet either. Okay? So without the 2 in there, is there anything going on? Things are getting up big pretty fast, but they're really bizarre. Okay? Any ideas? All right. Now, as soon as I glance down, yes.
So, with the 2 factored out.
What's that?
With the 2 factored out, each one is being multiplied by 3 plus 1.
Okay.
So you have 1 times 3 plus 1 is 4, 4 times 3 plus 1.
Oh, look at that. This is multiply this by that one by 3 and add 1. That one by 3 and add 1. That one by 3 and add 1. And let's see, yep, that one will work too. Yep, that would do it. So that would be 2 times 3 Okay, how do you say that? It's 3 times n Okay, the first one, you have to come up with the first one somehow. That's the big problem, child. This one works okay. That would be n minus 1 plus 1. That's not quite right. If you actually go back, it's a good pattern, but it's going to be hard to put down. I cheated because I looked at the book, but it almost has the same concept you had in there. I was trying to think of a way to make that happen. I'm sure there is. I just can't think of it right now. My head's not right yet. Okay? But think of what do 8, 26, 81, so again?
It's 80, not 81.
Yeah, okay. Yeah, but I'm thinking in my head 80. Okay, yeah. 8, 26. All right, let me make sure this one works. Oh, yeah, that is a minus 1. Yeah. From here on, okay. Add 1 to each of these numbers here, these numerators here. What do you get? 9. What are those? Okay, they are, but what else? Yeah, 9, 81, 27, 81. I didn't know 243, it wouldn't ring a bell with me, but isn't that 3 squared, 3 cubed, 3 to the 4th,
So
3 to the 5th.
3 to the n minus 1.
Yes, okay. It's, especially from here, it's, yeah, 3 to, yeah, I think you said it right, okay. So let's take out the 2. We might be able to go back and put the 2 in later and see how we could have gotten it that way. But this would be 3 to the n minus 1. Not n minus 1, but 3 to the n minus 1. Okay? Now let's see, how about for n equal 2, that works. N equal 1, yeah, that works too. Yeah, 3 to the 1 is 3, yeah. So it works even for this one, 3 to the n minus 1. There's your numerator. 3 to the n minus 1. Okay. With the alternating signs. Now, I wouldn't have recognized this with the 242, but let's just check that. 3 to the 5th power, make sure that is, well, the 81 times 3. Yeah, that works. Okay. So, now, was part of the question is decide whether it converges or diverges. What do you think? That certainly, this is a 2, a 4, 4 and a fraction. That's a 3 and a fraction. This is a 2 and a fraction. So it does seem to be coming down. Okay. But remember what we did before? We compared 2 to the n to n factorial. We compared 3 to the n to n factorial. The minus 1 is immaterial. Okay? But let's just think of this. This would be 3, the first several terms. 3 times 3 times 3 times 3 times 3 times 3 times 3. That's 3 to the n, or whatever n is. This will be, n factorial would be 1, 2, 3, 4, 5, 6, 7. Throw out these 3, and from then on, the denominator wins big time. So that's going to 0. That
means it's going to converge.
converge. It converges, and what does it converge to? 0. Yeah. Yeah. As n goes to infinity, that converges to 0. All right, that was a tough one. Okay. In time, you get to seeing those a little bit better. What they did was the absolute value one. If you can show the absolute value converges, then certainly the alternating converges. And that's what I did, was without thinking about it, I just dealt with the ignoring the sign, and that works for you. All right. Now let's, goodness gracious. What in the world will we mean by monotonic sequences, and then later we'll do bounded. Anyone have an idea of what monotonic means? Say again? I can't hear.
I'm sorry, you said monotonic?
Monotonic.
One?
Okay. Tandem. One direction. Okay? A monotonic anything is going in one direction. Either constantly increasing or constantly decreasing. Only going in one direction. The thing we just had that was alternating back and forth, not monotonic. Okay? But anything that's strictly increasing, strictly decreasing is monotonic. Trying to think if you've had that before anywhere. Yes, you did, I think. Precalculus somewhere there, and I can't think what part of that would be when we talked about monotonic. Okay. Now, bounded, what do you think that would mean?
Bounded by either the x-axis or the y-axis?
Bounded by what?
Bounded by either the y-axis or the x-axis?
It could be, but it could be any other line too. Usually don't do y-axis, but a bounded sequence means somewhere out there there's some maximum that you may approach it, but you never reach it. Or some minimum down here that you approach but never reach. That's what we mean by bounded. So you can be monotonic, but always increasing, but the rate of increase declines, and you're always getting close to never. Or you could have another one that always increases, but isn't bounded. Same thing with decreasing. That's what we're talking about here. We'll be talking about. So, definition of a monotonic sequence. A sequence A sub n is monotonic when its terms are non-decreasing, okay? Or when there's non-increasing, okay? Now, why didn't they say increasing or decreasing? Because if it levels out, that's not increasing, but it's not decreasing either, okay? Either direction, okay? So non-decreasing means it doesn't ever decrease. Doesn't mean it always increases, but it could flatten out. And this is non-increasing, meaning it's never going to increase, but that could flatten out. So that's why the equal signs are here. If you didn't have the equal signs, then you say increasing, decreasing. But with the equal signs, then it's non-decreasing and non-increasing. Okay. So the a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3. Yeah. So that's monotonically non-decreasing. And when a sub 1 is greater than or equal to a sub 2, then that's monotonically non-increasing. Okay. I like to think in terms of increase and decrease. I don't like double negatives, but okay, or single negatives even. So here's example 8. Determine whether each sequence having the given nth term is monotonic. What you say about A?
Well, it's -1 to the n, so that means it's changing direction or changing sign.
Yeah, okay, it's going to be either 3 plus 1 or 3 minus 1.
So it's not.
It's not monotonically, it's not monotonic. That's enough said, not monotonic. It's either going from 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. Not increasing and not non-decreasing. How about B?
It's always increasing.
Always non-decreasing, yeah. So, yeah, it is increasing, but it has a limit. What's its limit? Can you tell looking at it?
0.
Okay? If you divide numerator and denominator by n, this will be 2 over 1 over n plus n1. Because n is going to infinity. And 1 over n over 1 over n. Now n, remember, can't be 0. It's always a positive number. Okay? So you can divide by n. So if you divide by 1 over n, multiply numerator and denominator by 1 over n, this gives you 2 over 1 over n plus 1. It's n going to infinity. That goes to 0. 2 over 1. So that limit is 2. So it's monotonically increasing toward 2. Okay? You are right. But non-decreasing toward 2. How about C? First, is it monotonic? Now remember, n can't be, it has to be a positive integer. Okay? What you think? Start with n equal 1. What would you get?
You get
1. Okay? N equal 2.
4 over 3.
Okay? That would be a little bit greater than 1, right? 4/3. Okay? N equal 3. 9 over 7. That's still greater than 1. Maybe not quite as much greater than 1. So I think that maybe decreased a little bit. How about 4?
16 over 15.
Okay, that's definitely decreased from the previous. Still greater than 1. How about 5?
25 over 9.
Say again?
25 over 9.
Okay.
Oh wait, no, that's
No.
25 over 34.
71? Is that what I heard?
25 over.
1 over
31.
5. 2 to the 5th is 32, right? So 31. 25 over 31. That's definitely less than 1. So we started at 1. We went up a little. Then started going down. Monotonic? No. It started going up, then leveled off, started going down. From there it goes on down. Because that's approaching, remember we did that kind of, okay? So if you do 2 times 2, the denominator is 2 times 2 times 2 times 2 times 2 times 2. The numerator is anything greater than 5. No, we didn't do that. We did factorial. Yeah, but that's still. Here's a hint. Exponential functions may start slow, but they soon exceed polynomial functions. Factorials may start slow, but they soon exceed. At some point, will exceed exponential functions. Your polynomial functions, they're the most pokey ones, and yet they were the fastest things we dealt with before. Okay. So we got first not monotonic, second one is, third one not, right? Yeah. All right. And they show some graphs of those. Okay. definitely not the first one and the third one not monotonic. Sorry. I'm sorry. So the first one alternates between 2 and 4. Okay? Now, frankly, I almost find this, the fact that they smooth these curves out is just sort of nuts. These are just going deep, deep, deep. It's sawtooth. It's not sinusoidal. It's sawtooth. Deep, 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 deep. I really don't like the way they graph that, but it's okay, I guess. Okay? Trying to make it smooth and continuous. It's not. It's just down, up, coming up, down. Okay. So it's not monotonic. Next one, because each successive term is larger than the predecessor, even though it has a limit, but it's monotonic. We went beyond what they asked for. We found the limit. They didn't. Okay. Note, because n is positive, you can multiply each side of equality by n plus 1 and n plus 2 without reversing the inequality sign. I'm sure that's true, but why in the world does that matter? Okay. I guess that's somewhere else, okay? And how about this one, okay? Let's see, which one are they doing? Oh, I see. Okay, here's what they're saying. You can do this. So they're saying b to the n, question mark. Is that, if you do the n plus first term here, now this is one way to do it. 2 times n plus 1 over 1 plus n plus 1. Okay? So you're going to the next term here. Okay. Now, this is the inequality. I was going to say, what inequality are they talking about? This is the one they put here. Okay, if you multiply both sides of this by n plus 1, that's a positive number. Okay? Then this is 2n. This would be 2 times n plus 1 squared. And this would be over n plus 2. Still don't see why they want to do that, but let's see what they're talking about. Okay? That's equal to b to the n plus 1. Yeah, we see that. Now, what they're saying is multiply both sides by, I see what they meant. I misread it. They're multiplying by both of these factors. I thought they meant separately. N plus 1 times 2, 1 plus n times 2 plus n. And again, the question is why you would want to do that, but you're not changing the sign any. So if you multiply both sides of this by n plus 1 times 1 plus n times 2 plus n, okay, that will wipe this out and leave you a 2 plus n times this. And if you multiply this by, this denominator becomes n plus 2. Multiply that, you get 2 times n plus 1 times, I would have said n plus 1 squared, but they're saying 1 plus n times 2 n plus 2, which is fine. So that wipes out your denominator. Okay, now what you have here, 4n plus 2n squared this is mathematical induction in a sense, but really bizarre sense. This would be, let's see where they're going with it. Okay, yep, that would be 4n plus 2n squared, and this would be, yeah, okay. If you FOIL this, you get 2 plus, there's your 2n plus 2n is 4n, and then plus 2n squared. So for every n, this is true. Okay, I see what they're doing now. And this is always less than that, because these two terms are exactly the same. This has the 2 added to it. So, and as in is going to, we won't even go into that. Yeah, so this term is always greater than that term. Boy, that went around your elbow to get to your nose on that one. Okay. But that does give you a hint of how you can approach these. Look at the first term and then the next term and maybe even the term after that. See if you see a pattern. 0 is less than 2. For any n you happen to choose, that's always going to be true. So starting with the final inequality, which is valid, you can reverse steps to conclude the original inequality is also valid. It's kind of a proof by induction. This sequence is not monotonic because the second term is greater than both the first and the third term. Not completely obvious. Well, we did it and we saw it was. So it couldn't be monotonic. If you drop the first term from there on, it is monotonic. Okay. And then it's heading, heading towards 0 then. All right, how are we doing on time? Is it time? No. Okay, I didn't think so. That's what she said. Yeah, we've got. Okay. It's awfully close though, isn't it? 1 minute. Okay, that's what I was thinking. When he said, no, I thought, we were way off from it. Okay, I don't think in a minute I can do this, so we'll pick up here. I'm sorry, my brain is not well today. I don't think any of me is well today. All right, we'll pick up there in 9.1. We came that close to finishing 9.1. If I'd have been a little quicker, we could have done it. You can do any of the odds 5 through 9. They're all at Calc Chat. 9's at Calc View. Do 11 is at Calc Chat. I would suggest doing all of 13 through 16. They're all at Calc Chat. I mean, the odds are at Calc Chat, but you probably can do them both. Do 17 or 19, both at Calc Chat. 21 or 23, both at Calc Chat. 21's at Calc View. 25 or 27, both at Calc Chat. Any of the odds 29 through 43, they should all be at Calc Chat. 29's at Calc View. 45 through 51, they should all be at Calc Chat. 49's at Calc View. 53 to 59, they're all at Calc Chat. 53's at Calc View. Let me see if we've done 95. No, stop there. And we'll pick up the rest of those next time. I can't hear.
You go to the doctor about that cough.
It'll get over.
All right.
Okay. He says, okay. All right. Good deal. Sorry about the terrible sounding voice today. Hopefully it'll be better next week. Have a good weekend.